Hey, it's Zara. In the next two videos, we're going to be talking about optimization techniques, specifically gradient descent, which is widely used in machine learning. In this first video, I will begin by talking about convexity and why it is important in this context. And in the next video, I'll be diving more specifically into gradient descent and the intuition behind it. So let's start by framing the problem we want to solve. Imagine we have a model with some parameters, which we'll call W. These parameters define the model, and we want to find the values of W that minimize a certain function, called the loss function. The loss function measures how well our model is performing, and minimizing it leads to the best possible model. One common example of a loss function is the squared loss used in linear regression. The goal there is to find the set of parameters W that minimize the difference between the actual and the predicted values. In that case, minimizing the squared loss gives us the optimal solution known as the ordinary least squares estimator. Now, what we're going to do is think about optimization in a more general context, whether the loss function is the squared loss or something else. Our aim is to find the optimal parameters that minimize the loss. This brings us to the concept of gradient descent, a general and powerful method for minimizing any differentiable loss function. Before diving into gradient descent, it's important to understand the role of convexity in optimization. Convex functions are the class of functions for which gradient descent works most reliably. Generally, a convex function has a bowl-shaped structure, meaning it has a single global minimum and no other local minimum or maximum. Let's visualize two different types of functions to clarify the importance of convexity. We'll be talking about functions in 2D, but the concepts can be generalized into higher dimensions as well. Let's first consider a simple quadratic function like f of w equals w minus 3 squared. This is a convex function, meaning it has a single minimum at w equals 3. At this point, the gradient or the slope of the function is 0. This point is also the global minimum. In this case, setting the derivative function to 0 gives us the exact minimum. Now let's consider a function that has multiple peaks and valleys. For example, the decaying sine wave. This function has multiple points where the gradient is 0. But only some of these points are minima. Others are maxima or saddle points. In non-convex functions like this, setting the gradient to 0 doesn't guarantee that we've found the global minimum. It could be a local minimum or even a maximum. So convexity is key because it ensures that any point where the gradient is 0 is the global minimum. And this applies not only to 2D, but in all higher dimensions as well. When working with convex functions, we can confidently apply gradient descent and know that we're heading towards the optimal solution. Convexity can be formally defined in a few ways, and I'll go through the important criteria here. If a function is convex, then at any point w, the tangent line or the derivative at that point lies below the function itself. In other words, for any point u, the value of the function f of u is greater than or equal to the value predicted by the tangent line at w. This ensures that the function slopes upwards or stays flat as you move away from the minimum. Another way to think about convexity is to look at 2 points on the function, u and w. If the function is convex, then the function's value at any point between u and w will lie below the straight line connecting f of u and f of w. This means that the function curves upwards, creating that characteristic bowl shape. And the third criteria is the second derivative or the Hessian test. For twice differentiable functions, convexity can also be checked by using the second derivative. In one dimension, if the second derivative of a function is non-negative at all points, the function is convex. And in higher dimensions, we use the Hessian matrix, or a matrix of second derivatives. If this matrix is positive semi-definite, which means that all of the eigenvalues are non-negative, the function is convex. These three criteria are useful because sometimes it's easier to check one over the others. For example, the second derivative test is often easier to apply when working with smooth differentiable functions. And in the next video, we'll be discussing gradient descent in more detail.